Welcome back, guys. Now, in this section, we're going to look at something that might be considered a bit of an extension. It's something that I haven't really seen in any of the exam questions, but the ideas are really, really helpful, and they'll be able to help you solve a wider range of problems if we look at this problem here and how we go about solving it and setting it up and things like that. Okay, so in the previous video, we looked at how we can rotate our way of thinking so that it makes the problem slightly easier. Here we're going to extend that idea and actually modify the problem while keeping the details consistent. We're going to modify the problem to make it easier for ourselves to solve. Okay, and this is the problem here. You've got a mass M1 and it is pulling mass M2 up a slope. Okay, the mass M1 is being pulled down by gravity and it's pulling mass 2 along with it. It's connected via a string across a pulley. What we're going to do is we're going to turn this problem into a problem like this, into a problem like question 2. If you go back to question 2, basically it was a car or a vehicle pulling a caravan. Okay, we're going to turn a problem like this into a problem like that. Okay, now the way that we're going to do it is we're going to identify the forces that are acting on each of these objects. Okay, and then we're going to basically like sort of swing out those objects so that they're all in a horizontal plane. Okay, so let's look at the forces acting on M1 here. Well, it's being pulled down by gravity, so that's going to be M1G. Okay, force of gravity, mass times G. And at the same time, it's also got a bit of tension pulling it upwards. We'll call Ft. That's really the only forces acting on M1. Again, we're simplifying things by ignoring resistance, which a lot of the times we can. Looking at M2, there is a force of gravity also pulling it straight down. Okay, and then we're going to call that M2G. And it's being pulled up this slope with the rope so that there's tension there. We're calling that Ft. And there's also a normal force acting on this mass pointing perpendicular to the surface, which we're going to call Fn. Okay. Now, remember, we said set up your coordinate systems so that the accelerations of your objects point in a positive direction. So for M1, we could set down to be a positive direction. And for M2, we're going to set up the slope to be a positive direction, like that, because that's how it's accelerating. Okay. Now, imagine you've got this setup here, and you're going to sort of swing out the object. So this object gets swung out to there. So now it's horizontal. This object sort of swings out a little bit that way, and it's also horizontal. And now they're connected via the same string, just both objects are horizontal now. Okay. That's basically how we've set up this problem here. And we're just going to draw in our forces again. Okay, using the labels that we've given the objects in the original setup. So if I modify that, putting that as a positive direction. So now both objects follow the same coordinate system like this, because after swinging it out, these coordinate systems are basically the same thing. And we see that if we swing this out, this gravitational force is now going to be pointing towards the right. Okay, so M1 has a force pulling it towards the right, and the magnitude of that is equivalent to M1G, because that's the magnitude it was originally here. Again, you've got to remember that the objects themselves, they don't care about where the forces are coming from. They only care about the size and the direction of the forces. Okay, they don't care whether the force is a gravitational force or if it's a pushing force of some kind or whatever. Okay, so if we've identified that this particular pulling or pushing force has a particular magnitude, we don't care where it's come from. We just care about the magnitude, and we know that the magnitude is M1G. Likewise, we've got this tension still here, Ft, and that's it for M1. For mass number 2, drawing your forces for that, we've got tension pulling it that way. And remember, we can ignore the tension because these two tensions are going to cancel each other out overall. So we can ignore them later on when we set things up, but we'll put them in there for now. The normal force on M2 is going to point upwards because that's how we've set it up originally in our coordinate system. The gravitational force, though, points at an angle. It's going to point down this way. Okay, because if you go back to the original picture, the way that we've set it up in our coordinate system, it's pointing down towards the left. Okay, so that's M2G. And again, if we know this angle in here, okay, we can actually identify the components of the gravitational force in that coordinate system. Okay, that angle between our slope and our vertical is going to be equal to this angle over here. Okay, if you don't believe me, get a protractor and measure it for yourself. So if we now translate this over to our new setup, that's going to be there and there. Okay, and this is our original angle, theta. Okay, and that's how we're going to set it up. Okay, now we know that these two objects are accelerating towards the right, so we can actually write a net force equation for this system. So we can say that the net force is equal to the sum of the forces in the horizontal direction, which in this case are equal to, all right, what's pointing in the positive direction? We've got M1G. We can ignore the tensions, they're going to cancel each other out. What other horizontal forces have we got? Oh, we've got this horizontal component of the original gravity acting on M2, and we know that that is going to be M2G cos theta. Okay, so that we're going to subtract that in our net force equation. And that's really the only horizontal forces we've got acting on our objects. Okay. And what do we know the net force is equal to? Well, because we're dealing with a system of objects, we're looking at the forces on all objects in the system. The net force is going to be equal to the combined mass, which is the mass of the system, multiplied by their acceleration. You just got to remember the mass of the system is M1 plus M2 times A. Okay, this is our setup. Okay, this is what we're going to use in a question like this. Now, you may get a question where you've got, it's very, very similar. You've got, and I've seen this before, you've got a mass being pulled along a horizontal floor by a mass that is hanging here. Okay, and the angle between is just 90 degrees. So we can actually use this formula that we've developed here to solve a problem like that. And you might get one of these in your problem set. Okay, so just be aware of that. Okay, let's see how we use this in an actual question. So I've got these two masses. M1 is 10 kilograms, M2 is 5 kilograms, and they're connected as shown. There's an angle of 30 degrees between the slope and the vertical. And M1 is pulling this M2 mass up the slope at a certain acceleration. Okay, and our job is to calculate the acceleration of the masses. So what we've got is a situation that we've described exactly here. Okay, so we can think about this situation, we can swing out these masses so that they're both moving in a horizontal direction, and we've already identified the forces that are acting on those objects. So all we've got to do is apply this formula to this question. Okay, so let's write down that formula again. The net force is equal to M1G minus M2G cos theta. And just be aware that M1 and M2 have been defined as these particular masses. You may get a question where this is actually defined as M1 and this is defined as M2. in which case you're going to have to swap them around in your formula. Okay, don't get tricked by that. You've really just got to make sure that you understand where this formula came from and what these terms in this net force equation represent. Okay, but you can ignore them. And our net force is equal to the mass of the system, m1 plus m2 times the acceleration. Okay, now our job here is to calculate the acceleration of the masses. So we're just solving for A. Now look, we know m1, we know m2, we know theta, we know g, we know m1 plus m2. We've only got one unknown in one equation. So it just becomes a case of rearranging and solving for A. And in fact, we get A equals m1g minus m2g cos theta over m1 plus m2. Putting our values in, m1 is 10, g is 9.8, minus m2, which is 5, times g 9.8 cos angle, which is 30 degrees, and all of that is over the combined mass, which is 15. Okay, pop that into your calculator, make sure your calculator's in degrees mode, and you get 3.7 meters per second squared. Okay, so it is a little bit of an extension. What we've done actually is generalize a set of problems to include anything that's being, anything like this where you've got a mass being pulled along by another mass and there's an angle between those two things being pulled. You can actually use this formula to analyze things where it's completely horizontal to begin with, in which case the angle between these two masses is 0, in which case you get cos of 0, which is 1, and you get m1g minus m2g. That's it, all right? Or you could get one that is 90 degrees, in which case you'd get cos of 90 degrees, which is 0, and this term will completely disappear. Okay, so have a think about that. Go back and watch the video. Ask for help if you need it in class, all right? Just some points to remember before we finish this set of videos for just general force problems. Friction always opposes, or at least tries to oppose, the direction of motion. So if something's moving towards the right, friction will act towards the left. You've just got to remember that no acceleration implies no net force. If something's not accelerating, then there is no net force, at least in the direction that you're talking about. So if something is not accelerating towards the left or right, there is no force, or no net force, rather, in the left or right directions. It might still be accelerating up or down, in which case there will be a net force up or down, okay? And also that the simplest coordinate system generally represents the net force as positive in either the horizontal or vertical direction. So that's what we've been doing. We've been setting up our coordinate system so that the acceleration points in a positive direction. It is not pointing at some weird angle with our coordinate system. It is either pointing horizontally or vertically, in which case your net force will also be pointing horizontally or vertical, and that's going to make things a lot simpler for you to analyze in terms of these two-dimensional force problems. Okay, so we're going to leave it there, and in the next series of videos we'll start looking at circular motion. So go back, watch the videos, read the book, read the notes, do your practice problems, ask for help in class. See you next time.